This module is about electrostatics, fields, and forces. It's the basis for virtually everything we're going to talk about in this course. Electricity can be thought of as, or electrostatics can be thought of as electricity at rest, or static electricity. There's really no current flow. We call the name given to a fundamental quantity that underlies all these electrical phenomena, we call charge. There are only two types of charge, and we've labeled them positive charge and negative charge. Could have labeled them anything. We could have labeled them plus and minus, yes and no, but we called them positive and negative. Electrons have a negative charge, and protons, the other charged part of an atom, have a positive charge. Neutrons have no charge. All these charges are exactly equal. So every electron has exactly the same charge. And not only that, but every proton has the opposite exact charge. So all protons are exactly alike, and all electrons are exactly alike. Like the mechanical forces, electrical forces affect motion in accordance with Newton's second law. The electrical force between two objects is very similar to the gravitational force, but it's billions and billions of times stronger. In physics, we call the electrical force the strong force, and we call the gravitational force the weak force. Like the force of gravity, the electrical force is inversely proportional to the square of the distance between the two charged objects. And no material is necessary in the space between the two objects. Unlike gravity, which only attracts two objects toward one another, the electrical force can be either attractive or repulsive. Like charges repel, unlike charges attract. The symbol for charge is Q, and the units of charge are in coulombs, after Charles Coulomb. 1 coulomb is the charge on 6.25 billion electrons. Or, it's also the charge on 6.25 billion protons. Here's a picture of how Coulomb's law works. Q1 and Q2 are the charge in coulombs on objects 1 and 2. And d is the distance between them. D squared is the square of that distance. That means that distance multiplied by itself once. This constant K is equal to 9 times 10 to the 9th Newton meters squared per coulomb squared, and it's true everywhere in our universe. It's a universal constant, always has this value. We have an exercise here I'd like for you to read through and try to do. What you're actually doing here is you're calculating the coulombic force between two objects, two electrons, separated by a distance. Turns out that distance is 1 times 10 to the 3 meters, or a millimeter. So just to show you or demonstrate through your own discovery and calculation that the charge force, the electrostatic force, is much, much greater than the gravitational force. And you'll get to use your powers of 10 and your scientific notation in this exercise. Charge on an individual electron or proton can't be created, changed, or removed. For that matter, electrons and protons can't be created, changed, or destroyed. Therefore, total charge in a closed system can't be created, changed, or destroyed. We say that electrostatics is therefore a quantum-based phenomenon. We can't move charge, but we can move subatomic particles. An atom that has lost an electron is positively charged. Sometimes this is called an ion or a free radical. And an atom that has gained an electron is negatively charged. Protons generally don't move between atoms, but atoms move. They move in chemical reactions. The area in which the influence of a charge accumulation is significant is said to be enclosed in a force field. The intensity of such a field at any point is the ratio of the magnitude of the electric force to a unit charge at that point. An electric field, like the electric force, is a vector quantity having both magnitude and direction. Here are some pictures of electric fields represented by lines of force, which show the direction and to some extent the magnitude based on their density, that is how close they are together, the magnitude as well of the electric field. So you can see that electric fields can also not be, even though the vector, if you connect the positive to the negative charge, the lines don't have to be linear. They can be curved lines like this. Electrical potential energy is the energy stored when I bring a charge, when two charges together. It's like pulling back on a slingshot or cocking a plunger gun. The force on charge Q is K Q1 Q2 over D squared. So work is done, and work is normally the product of force times distance. So the distance through which the force acts. So potential energy in the simplistic forms, you really need calculus to do this. Potential energy is K Q1 Q2 divided by D, since one of the D's in the denominator cancels with the D that's multiplied by the force. So I think you can see that with a little simple algebra. And electrical potential voltage is just the amount of potential energy per charge. And so that's explained in this slide. And you can see that since that's equal to, since the voltage is equal, the voltage would be equal, the potential energy is K Q1 Q2 over D. So if I divide that by charge, in other words, potential energy per unit charge, I would get K Q2 divided by D, where we're assuming that Q1 is a singular charge, a charge on an electron or a proton. So now you have a definition of voltage. Voltage sources are necessary to drive a sustained current, and we're going to be studying that in Unit 2. The most easily understood and most common voltage source is these days is the direct current DC battery, and your home's probably full of them, and sometimes my pocket's full of them. This being the case, we use some typical DC voltage source values like 1.5 volts, and 3 volts, and 6 volts, and 12 volts in the examples of simple circuits we will discuss in our study of electricity. Hope you've enjoyed this presentation.